Okay, for those that have already tried to watch the previous movie from today, session 18, I apologize. There was something wrong with the sound. I still have not figured out how it happened, but I'll do this movie again so that you have one with sound. Okay, so alternating series. What are we talking about? We have seen this notion of alternating sequence, right? There was a sequence that had signs that change from minus to plus and so on. So a very simple example would be this sequence. And we already noticed that if you take the series, and yeah, before I say this, how do we list these numbers? Well, we can write the general formula as minus 1 to the power n, because that's how even ends then give even power plus 1, and odd ends give an odd power minus 1. So for instance, this sequence here would be given by this thing if it starts with A1. Okay, so, and then if we would look at this series here, this was an example of a series that we know it was divergent. Go back, look where it is, but you can easily see this because the partial sums are 0, 1, 0, 1, 0, 1. They don't have a limit, and therefore the series is divergent. So today we want to talk about series of this type, and the first one I want to consider here is this one. Again, we have start here from 1 because otherwise it makes no sense. So what is this? This is the general formula, but very often, and I accept that if you write your series rather spell out what they are. So this is the first one. For n equals 1, you have a negative 1, and then you would have a positive, right? And then in the denominator 2. Now again a negative, but in the denominator you have 3, 1/4, and so on. I hope, make sure that you understand how I got these various elements of the sequence. And so you see here what we get is kind of the harmonic series, except that we have pluses and minuses. So this is therefore called the alternating harmonic series. Now the harmonic series, what we know about that? Well, we know it's divergent. One way to see that is because it's a p series with p equal 1. What about this one? Well, here is now the criterion that we're going to consider. And so this is the alternating series test. What does it say? So in general now, as I said, an alternating series would look like something like this, right? You would have the part here that makes the signs, and then these ANs are positive numbers. So, okay, let me write it up here. We have something like this. By the way, this power n here could also sometimes be n plus 1 or n plus 2, just depends on what we want. When even ones odd, or we want the even ones to be negative 1 or the odd ones to be negative 1. That depends on the situation. So, so what we have here for is that the AN, of course, are positive now. So I think of the ANs as the positive part, right? Ignoring the sign. Now there's 2 more conditions that I have to impose, but I'm going to put in parentheses. They're important, but not for us, because all the examples, except for sines and cosines, will automatically satisfy this, and that is that the AN has to be decreasing sequence, so the values should be getting smaller and smaller, and positive, yeah, well, positive I said that, yeah, okay. So that's the only 2 conditions that I really need to make sure that are satisfied. Okay, and so what's now the general result is if the limit for n going to infinity of the ANs. In other words, notice that the difference between the series and this is that I have now ignored these negative signs. Sometimes they are there, sometimes they're not, but I mean, depending even or not, but that's what I look at. So I look now at the limit of AN. If this limit is 0, then the series converges. Now you ask, what about if the limit is not 0? Well, we know always that if the limit of a series is not 0, then we have divergence. This is so-called divergence test. One of that we talked about all the way in the beginning. We said it's not important because who is interested in divergent series? So the most important thing is that this test works for alternating series, namely if the limit is 0 then we get convergence, but I'm stress this very strongly, this is not the case for arbitrary series, okay? So let's look at the harmonic series, and I'll give examples what I mean with it's not true in general, but let's first look at alternating series, and let's look at this guy. Okay, so the question is this alternating harmonic series, let me write it now like this, it's the same thing, right? Is this convergent? That's the question. So what you have to say, well, we have to check that it is an alternating series. Well, that's given by these signs. This part here that it is decreasing, I said, well, you see it's a decreasing function, but I'm not going to insist that you check this. All the examples, all the tests, all the problems that you're given are automatically this. Okay, so we're going to ignore this condition. Okay, so what we need to do therefore, well, we need to calculate the limit of what? Well, you take this guy, but ignore the sign. So we look at this limit for n going to infinity. Now it's a very easy limit, right? It's 1 over infinity, that is 0, and that's exactly what we wanted. If the limit is 0, we get convergence. Okay, so this means that the alternating harmonic series is convergent, yes. Whereas, notice that this guy is divergent. Because why? Because it's a p-series where p is 1. You see that? Okay. But of course, the limit of 1 over n is 0, right? It's the same limit. So you notice that it is important that we have these negative signs here. Without the negative signs, it would not be true. Okay. So I'm going to give you a couple of more examples. I don't want to look at the textbook if you want to know why exactly is this the case, but we were more interested in applications, applying these tests rather than proving them. Okay, so here's my first example of another type of alternating series. And of course, as I said, the alternating series you immediately recognize just by these minus 1 to the nth. Okay, so this is an alternating series, so is it convergent? That's the question again. Any answer? So by the alternating series test, and that's of course, when you do this in general, you're going to have to always mention that this is what you use. We are now in the topic of alternating series, so all the problems are going to be that, but okay, so we have to calculate the limit for n going to infinity, ignore the sign, and so what left is this. Now, we know how to do this. We can do L'Hopital, but the most obvious way is divide top and bottom by the highest degree term, which is n here. Now remember, when you divide, it means divide everything. So what we have is the limit for n going to infinity, 3n divided by n, that's 3, plus 4 divided by n, 7 plus 5 divided by n. And then, why do we do this? Because these reciprocals, because 1 over infinity is 0, or 0, so we're left with 3 over 7. Now that's not 0, and this therefore we have divergent. Okay, I repeat here, this is the condition. Let me box it a little bit, and I can keep going back to it. Okay, all right, so this is an example where it's not. I'll give you another example where you have to calculate a little bit more, do a little bit more calculation in the limit. Again, it's an alternating series, that the series decreasing. Again, as I said, you can assume that is true. And okay, so what we need to do, alternating series test. There's only thing we want to do, we take the limit for n going to infinity, n over 2 to the n. Now, of course, if I plug infinity, this time I get infinity over infinity. That's an indeterminate form. But you remind you of these things. If you don't exactly know anymore what I'm talking about, go look this up in your Calc 1 book. I mean, you can download the Calc 1 book. So what we need to do, well, in this case, I would recommend L'Hopital. Well, I only know how to do it is using L'Hopital. So we're going to do L'Hopital. Now, technically, to do L'Hopital, you actually have to write it as a limit of a variable, a function. It's easily done, and so now what we do with the L'Hopital, so in fact L'Hopital only happens here, is I'm going to take the derivative of the top, which is 1, and the derivative of the bottom. Remember, the derivative of ex is ex, but the derivative of 2 to the x is 2 to the x times ln2. This is extra coefficient that comes in. Okay, so if I plug in infinity now I get 1 over infinity, which is 0. Aha, convergence. So this is now a convergence series. All right, so and there will be a couple more problems, homework problems like that. Now, this is the second part of this section 5.5 is about what is called absolute or conditional convergence. So you see the two terms, absolute and convergence, okay? The two terms are kind of negation of each other, but they're both about convergence. So we're going to distinguish the type of convergence. And what is this? So we're going to have a series, summation an, and again, from n going from 0 to infinity. Let's, for simplicity, start from 0 this time. So what does it mean? So absolute convergence, it's always a mouthful, and so we're going to just say AC, absolute convergence, and conditional will be CC. Okay? So what does that mean? So absolute convergence, let me start with that one. Absolute convergence means, so AC means the following. That take this series. Now, I haven't said anything about the ANs. The ANs could be anything, meaning they could be negative. They can be alternating, or they could be like the first 5 are negative, and then the next 3 are positive, and then a couple of negatives again, and so on. So really anything is possible. If now you take absolute values, now, so in other words, you ignore all these signs and just look at this series, if this series is still convergent, AC means that this series is convergent. In other words, the series where you ignore the negative signs. So what does CC mean then? CC means, well, the negation of this, that this is a divergent series, but it is, no, it's convergence. So if this is divergent, why are we calling convergence? Because there's two conditions for CC. That this is divergent, but that the original series is convergent. So what is this? How is this even possible? Well, it's very much possible. Here's an example. Look at this. I actually worked it out for you already. I'm gonna circle it here. Here, look at this. This series here, what are the ANs here? Minus 1 to the power n, 1 over n. The series is convergent. Now what's the absolute value of this thing? If I take absolute value of this thing, I get exactly this, right? Okay. So the absolute value series is divergent. It's exactly the situation that we're talking in. If you take absolute values, you get divergent, but without the absolute values, you get convergence. So what this means is this series, 1 over n, is conditionally convergent, CC. Because if you take absolute values, it isn't. If you look at the series as is, with the negative signs, then it is convergent. So CC, it does happen. Okay, then you say, okay, perhaps AC is now weird. And there's another thing that you might question here is, okay, here I explicitly said CC means that the series is convergent. I didn't even say that's for absolute convergence, but it follows from it. So this is something, again, I'm not going to prove, we just accept this, that if you ignore the signs and you're convergent, then actually the original series is also convergent. Okay? So then you don't have to, that's why we don't talk about this second condition in the first case, because it's automatically true. Okay, so let me do some examples. It helps if I do more examples to understand, to see the subtlety that's going on here. So here's my first example. Well, other than, of course, the harmonic series, alternating harmonic series. Here is this one. Summation minus 1 to the n, 1 over n squared. Let's do this one. Okay, so question, what is it? So what is it now? Now we have three options, right? AC, CC, or divergent. Because we split convergence in two types, right? I remind you, the two types I have, AC and CC, both imply that the series is convergent, okay? But they say something else. They say they differ in the fact when you ignore the signs. It's these two guys that now are make the difference between AC and CC. Okay, so How do you tackle this? Well, normally you do two steps. Sometimes you don't need to do that, but let's keep that subtlety for later. Just let's do plain, because the first step is rather simple. This kind of question you're only going to be asked when you're dealing with alternating series, so we're going to do the alternating series test. And so, okay, what does it mean? That means I have to take the limit for n going to infinity of, so this is the series, and then we ignore the negative signs, so we get minus 1 over n squared. Now that's an easy limit, that's 1 over infinity, that is 0. Okay, so alternating series test works. Just remind you, alternating series, I'll put it in the color that you see it a bit better here. That's the alternating series test. So that worked, so we have convergence. So now the other box here. What about this? Are we dealing with AC or CC? That is the step 2 part. So what did you do in step 2? In step 2 now, it means we have to look at what happens in this case, where we have the absolute values. So we do that. So we take the absolute values, which again means, I'll write it up. So minus 1n, 1 over n squared, and we take absolute values. Now, you might be thrown off by the symbol absolute values, but it really is just means forget about the negative sign. So what we talk about is just this. But you said we just did that. No, you didn't. What you did was the limit of 1 over n squared. Now you're looking at the series 1 over n squared. So don't confuse these two things. So how do I figure out what happened with this? Well, I see it. You see it? Okay, if you don't, pause the movie and figure it out. It's a P series, and what is P here? P is 2, which is bigger than 1, which means therefore convergent. Yeah, go back. Is it bigger than 1? Is it smaller than 1? Is it not 0? What is it? It's this. Bigger than 1 makes convergent. So what does it now mean? If we ignore the sign, we still have convergence. So it is absolute convergent. Right? That's it. And in some sense, I didn't need to do step 1, because step 2 already told me that the series, well, being absolute convergent implies convergence, and that's what I got in step 1. But you don't know that in advance, so very often it's better to just do both steps. Okay. Another example, this is my last example then, summation minus 1n, 1 over n ln of n. Now I have to go from 2 to infinity, otherwise I'm running in trouble here with the first few terms. Again, an alternating series, so the question AC, CC, BC make the divergent makes sense, right? Okay, so step 1, it's an alternating series, so I can take the limit. So, and that's why I'm saying always write what test you're using, alternating series test. So I take the limit for n going to infinity. What do? I ignore the negative sign. Okay, so I get 1 over n ln n. And then that's easy, right? That's a very easy limit, because if I plug in infinity, this is infinity, but the ln of infinity is also infinity. So the whole thing is just infinity, which is 0, which by the alternating series test, go back all the way up, alternating series test means convergence. Okay, so we have a convergent series in step 1. But now, is it absolute or is it conditional? And that's where we have to now look at the series with the same thing now, is now because we ignore the negative sign, the same formula, right? But it's now a series, not a limit. Okay, I hope you see the difference between what happened, this symbol and this symbol here. They're totally different meanings. One is just a limit, the other is really a sum. Okay. What should I do here? What methods do I have? We haven't seen that many yet, so we have to look a little bit at the possibilities here. But one possibility that we have, you might think limit comparison actually doesn't work, because we have a mixture of n's and ln's. Ln's are not they're not geometric series and they're not P series. So what can you do about that? So here what we only can do is the integral test. So I'm going to use the integral test. I'll write it here. So the integral test. What does it mean? It means that I have to look at this as a function. I can write the function down. So that is 1 over x ln x dx, and then go from 2 to infinity. It's an improper integral. And of course, the improper integrals, the first thing we also should do is make it into a proper limit of a proper integral. Okay, so that's what we have to calculate. Now comes integration. Okay, we have to integrate this. So let me write down the integral. When I have to do integrals, especially improper integrals, I kind of like to do first my indeterminate integral separately, and then I fill it in. Let me perhaps give myself a little bit more space here, so that I can fit it in later. Okay, so here I'm going to do this integral here, 1 over x ln x dx, right? That's the integral I'm talking about. Okay. You might be tempted to say, oh, integration by parts, right? Because there's an algebraic and there's a logarithm. It's in the denominator, and this integration by parts only works really for very, very nice situations where you have just a logarithm, just an exponential, just a sign. Nothing more complicated than that. Times, of course, an algebraic, but okay. So that doesn't work. I hope you see it. The solution here is substitution. I'm going to use substitution, namely u is, what is it? U ln x, right? Because if I take du, it is 1 over x dx. And let me show you why. What we need in substitution is that everything else should be the du. And that's exactly what's left, right? What we have the ln x, that will become u. So, okay, so I can plug everything in, right? So what do we have? The red part, that is 1 over u now. What about the 1 over the green part? Well, all that together is just du. Okay, so you see where everything comes from. Now this is an extremely easy integral. That's just ln of u, plus a constant if you want. And u was just ln. So it's the ln of x plus a constant. But okay, that's not important because we're going to go here now. So this is let me give myself a bit more space again. This is the limit for t going to infinity of from 2. So it's the indefinite integral is ln of x, and I have to now put this between 2 and t. So here, plug this in, the endpoint, the fundamental theorem of calculus, right? That is ln of t minus the ln of 2. No, I don't need to write that. So this first one, that's just a number. That's fine. So we're good. Okay, but what about this one here? It's not so hard this time. If I plug in infinity, I get the infinity. The log of infinity is still infinity, and then so the whole thing is just infinite. What does that mean? Well, that means divergent, right? That's exactly how these integral tests work. If your integral would have been convergent, then your sum would have been series would have been convergent, but the other way around, it's divergent. So, what's now the final conclusion here? Step 1, if I look at with the signs, the original series is convergent, but without the signs, it is divergent. So, you see, we're in the case of the second one. So this is, where am I here? Let me write it up. So this series is conditionally convergent. Okay, so I'll post some homework problems and then solutions to the homework problems, and then we can look at more problems. And there will also be a quiz soon about this. Soon, well, in a few perhaps sessions, perhaps next week or something, that I will announce everything on. Always give you at least one day, one session ahead. All right. Okay. So sorry for those that have been trying to listen to this thing without sound. I try to keep the same examples. I might have done it slightly differently. And don't forget to leave a comment.